Hi, and welcome back. So in this lesson, we're going to look at what evidence do we need in order to prove what type of quadrilateral we have given 4 coordinate points. So let's start with slope. The slope formula, if you recall, is the change of y divided by the change of x. More commonly, the rise or run. Now, when we look at that from a formal point of view, it's our y2 subtract y1 divided by x2 subtract x1. We'll look at that a little further. So for each one, if I want to prove that red and blue are parallel, well, that means they're going to have the same slope. So I can go from either point. I can go from this point this way, or I can go this point this way, as long as I keep the same order of points. So just to show evidence of that for blue, I have here 6 subtract 2. So my change of y divided by 3 subtract -3. And I'm not really going to have the writing plus, but you can if you want to subtract the negative. So here I have 4 over 6, which simplifies to 2/3 as my slope ratio. Now if I go the other way, and say, oh, just want to double check to make sure, and I go from this point left to right, I can say, well, 2 subtract 6 divided by -3 subtract 3, and now I get -4 over -6, which equals a positive 2/3. So what I'm showing here is as long as you're consistent with your points, and you keep that order, it is all going to work out. Now, red line here, again, I'm going to choose any of 2 points, so I'm going to red. The rule is to see if they are parallel. They look parallel, but I need to prove it. So -4 subtract 2 divided by -3 subtract 6. Here now I have -6 or -9. 5 and negative divides out, and then 3 over 2 over 3. So what that shows me here is that these two are parallel to each other, which is helpful because if I want to talk about a parallelogram or a type of parallelogram or a trapezoid, well then they have those parallel side features. Well, the green line looks a little bit different because it intersects both of them. You might be thinking, well, they're not parallel, but there's something different about it. So when I calculate for green, I see here, and again I'll just go left to right to be consistent. 2 subtract -4 over -3 subtract 2. And double check it here. 2 subtract -4. Oops, excuse me, I chose the wrong point there. The spot and was -4. So let me just restart it. So again, left to right, that's going to be 5 subtract -4 divided by -4. And here I get positive 9 over -6. That simplifies to -3.5. So you might notice something. Well, with our red line and our blue line, these are both positive. Positive, so now I have a negative slope. So the first thing I see here is that they are opposite. And that's my sign, plus or minus. And then the fraction is flipped, and we call that the reciprocal. It's opposite and reciprocal. And where this helps us is that if 2 lines are opposite reciprocal, they are perpendicular to each other and form a 90 degree angle. We use a little symbol like this instead of T for perpendicular. So we get these 2 pieces of information that we're going to use in our truths. Parallel lines have the same slope, and perpendicular lines have opposite reciprocal slopes forming 90 degree angles. And that's helpful because squares and rectangles, they have vertexes at 90 degree angles. And as well as heights and rhombus of a square, their diagonals meet and they form 90 degree angles. So we can look at using this as we progress into our proofs. Next part here is we're going to look at the activity that we did. Let's go through here. So I'm just going to guide us through it. So we have here our shape and our line segment, and I have a vertical line, a horizontal line, or if I go this way, same thing. We see here that no matter what, form a rectangle. And with that rectangle, the horizontal distance is 5 units, and the vertical distance is 12 units. So I think if this is a right triangle, we'll then 5 squared plus 12 squared equals to S squared. And I go from here, calculation from 69 equals to the square root of R S squared, and it tells me 13 is going to be the length of R S. So it doesn't matter when you're drawing this, which way you go. What this does show us is that to find the length of a diagonal given 2 points, you just need to know their lengths. So how do you find their lengths if you can't necessarily draw them out? Well, another way to do that is to set up this general rule. So let's start here. Again, we're going to give you 2 segments, and we're working here. Horizontal line and the vertical line, and I'm going to call this point K over here. So let me get my point K. Sorry, point L, excuse me. And L has gone to the right to X2, and it hasn't gone up the same as what I want. So we need to point K. So for us to calculate the distance for LK, what we want to look at is what's this distance? Well, these stay the same, but these change. So their distance is going to be the y2 subtract y1. And the same idea here is that our x changes, but our y stays the same. So our distance for JL is going to be x2 subtract x1. And we look at this and we see the fact that this is a right triangle. We look at the right triangle, so we go across the line. So we connected them there with a diagonal, and that tells us that if I have 2 legs, I can use a Pythagorean theorem. You know, leg squared plus leg squared equals hypotenuse squared, or more commonly, a squared plus b squared equals c squared. So this side now becomes one of my legs. And this is the other leg. What I can do is I can plug that in, this quantity, this diagonal. Here, I can plug that into my formula and figure this out. Scroll up a little. So my distance, in terms of a squared and b squared, well, a is just going to be, let's take Q4 variables, x2 subtract x1 squared plus y2 subtract y1 squared. And if I go through here algebraically, and I want to solve to get d by itself, I take the square root of both sides. And I can't take the square root of this binomial, but I can do this fully simplified. I get the formula here as d, which is going to be our distance, equals to the square root of x2 subtract x1 squared plus y2 subtract y squared. And you can change the order. You put the y2 on those first here. The idea is that when you square them, they're staying there. So this is the distance. Look at this in terms of Pythagorean theorem. This would be no different than me saying C equals to the square root of a squared plus b squared. And then A and B are just those distances in the horizontal and vertical change. So let's put this into practice real quick. Then focusing on getting the exact lengths and no approximates at the end. When you use your calculator, put the radicand value in your calculator to do your computation. So first thing is say our sum, plug it in, and we go from there. So d equals the square root of, and we plug in my values. So I start with my x values just to be consistent, and I'll go from a to b. So negative 12 subtract 8 squared plus 17 subtract 3 squared. There, we get the square root of negative 4 squared plus 13 squared. Now on your calculator, remember that negatives will change. So if I have negative 4 squared, that is not going to be equal to the quantity negative 4 squared. So what you want to do is make sure that you're working the right order of operations. This is like saying negative 1 times 4 squared. And this is like saying negative 4 times negative 4. So here I would end up at negative 16, which is not equal to positive 16. So use your grouping symbol on your calculator. So we get d equals to 416. We got to our factor tree. And then we're going to break this number down because we want to get the exact value. I told you it's good to use prime factorization, but the best trick is to find is divisible by a perfect square. And this is divisible by 16, which is a perfect square, times 26, and 26 breaks down to 2 and 13, which are both primes. So when I get to d here, d equals to the square root of something.